In exercise 21.15, they're asking you to draw a plausible mechanism for the following transformation. When you look at the changes that happen in this molecule, you'll notice that on the one hand, you have this oxygen with a methyl group and a cyclohexane, and that still stays there in the final product. If you look at the other molecule, you'll notice you have a carbonyl with a methyl group on it, and you still have that carbonyl with a methyl group on it. What has changed in this is the other thing attached to the carbonyl carbon. The chlorine has been replaced by what we now recognize as a nucleophile. So this alcohol. So we're taking an alcohol, we're combining it with an acid chloride. We're going to do a nucleophilic acyl substitution reaction that turns that into an ester, so that the alcohol takes the place of the chlorine. Okay, well, let's draw the acid chloride. This is very reactive, as we've discussed before, both because the carbonyl carbon is bonded to oxygen twice and to chlorine, which is very electronegative. And so the carbonyl carbon is really slightly positive, and also because the chlorine is such a good leaving group. So conceptually, we can think about that as a leaving group. So this is really reactive. It's so reactive that you can even take a mediocre nucleophile, like this carbon chain, and the oxygen there, which only has a slightly negative charge, it doesn't have a full charge, so technically it's perfectly fine being by itself the way it is, but this is such a good electrophile, these acid chlorides are so reactive that that nucleophilic oxygen attacks the carbonyl carbon and pushes the pi electrons onto the most electronegative place nearby, which is that oxygen. And so if you're classifying that step in terms of the four curved arrow patterns that we've learned, you would recognize that as nucleophilic attack. One of the essential steps in any substitution reaction. Okay, well, after that first step, you have your famous tetrahedral intermediate. So this pi bond will break, the electrons will form a new lone pair on this oxygen, which now has 3 lone pairs and therefore a full negative charge. The lone pair on this oxygen will form a new bond, and so you'll have this molecule here. The oxygen there has 3 bonds, and therefore it has a full positive charge. Okay, well, the charges give you information about what needs to be done. Now, if this incoming nucleophile needs to be stabilized, this is unstable. So how can you change the stability or reactivity of things? You can do a proton transfer. So here, to stabilize that oxygen, you can get another alcohol molecule. That's the only molecule that's in here, and the oxygen on it is slightly negative and can act as a sort of base, where it attacks the slightly positive hydrogen and the electrons snap onto that oxygen to stabilize the positive charge there. And this is going to be an equilibrium reaction, because there's no reason why this oxygen would be more unstable or prefer to have the hydrogen on it than this one, so they'll both fight over it in an equilibrium, create an equilibrium. But what you get after that step is a stabilized nucleophile. You have a stable tetrahedral intermediate. So this hydrogen won't be there anymore. The electrons in the bond to it will be a lone pair just on the oxygen. That will stabilize that positive charge, and somewhere in the solution we'll have that alcohol with an oxygen with a positive charge, an oxonium ion. So we have our tetrahedral intermediate now. We have an awesome leaving group. We don't have to turn that into a better leaving group. It's already amazing. And so this oxygen at the top, which is has a full negative charge and is therefore unstable, sort of just flapping in the wind, feels the slightly positive charge on this carbon. And it is significantly slightly positive because that carbon is bonded to an oxygen, a chlorine, and a carbon, 3 very electronegative elements. So it's losing electron density at each of them, and the oxygen with the full negative charge wants to make another connection to it. One of the lone pairs snap back down and try to form a bond. Now, the problem is this tetrahedral carbon already has 4 bonds. So if it's going to form a new bond, something has to leave. The best leaving group here is the chlorine. So the chlorine pops off of the molecule. And what we end up with at this step is a pi bond to the oxygen, single bond to the other oxygen, and then we have our cyclohexane ring. And that is the product that they wanted us to explain in this mechanism. So that is the product of this nucleophilic acyl substitution. That's what they gave us here to explain. So ultimately in this reaction, we replaced the chlorine leaving group with a sort of alkoxy group, carbon chain bonded to an oxygen. We replaced it with effectively an alcohol. We did the 2 essential steps of any substitution reaction. We did nucleophilic attack and loss of a leaving group. Oops. That was this last step here. And in between there, in order to stabilize the nucleophile that came in, anytime your nucleophile has no full negative charge and looks neutral, after it creates a new bond, it will have a positive charge, and you'll have to stabilize that with a proton transfer. So that's why we did that proton transfer there. But otherwise, we just had the essential steps for a nucleophilic substitution, nucleophilic attack, and loss of a leaving group, and that allowed us to turn this alcohol and this acid chloride into an ester.